Dear students, as a part of the computer integrated manufacturing course, it is very interesting for us to know about the assembly. Assembly is the end operation of a manufacturing unit. When you manufacture various parts, the parts being assembled to give you a final product. Unless the assembly is done, the final product is not seen the day of the light of the day. Thus, assembly is very important activity of a manufacturing system, whether it is computer integrated manufacturing system or a simply manufacturing system or manually operated manufacturing system. Hence, let us discuss the assembly part of this. As a part of assembly, we need to study the manual assembly as well as automated assembly. First manual assembly comes, then automated assembly comes, because in the manual assembly systems we need to know what is called as line balancing, how to do the line balancing, what design aspects need to be considered in line balancing. Once you know these things, the automated assembly systems can be easily extendable. Thus, let us devote this class exclusively for manual assembly lines. Coming to the lecture on the manual assembly lines, I am going to discuss like fundamentals of manual assembly lines, analysis of single model assembly lines, line balancing algorithms, other important considerations in assembly line design, alternate assembly systems. Let us discuss these things in detail. Work system consists of multiple workers organized to produce a single product or a limited range of products. Assembly workers perform tasks that at workstations located along the line of flow of the product. Usually a powered conveyor is used. You take simply a TV assembly or a motor assembly line. Normally assembly is done in a typical line fashion. When the the base part is loaded at one end, and when the base part is moving, the other parts are added to these things. And this movement of part from one line to the one end to the other end is called as assembly line. When the parts are moving from one end to the other end, all other parts are added at various locations, which are called as workstations, and at various positions or at various points where the assembly is done, okay, or which is called as, these places are called as workstations, and all the parts are added. When it comes to the end of that, you get the final product. That's called as a completed assembly product. You get it. You can do it in a line fashion, or you can do it in a U fashion, or you can do it in a looped fashion. Anything is okay. Anything is acceptable. Depending upon the space constraints, you need to design your system, your manufacturing assembly manufacturing system as per the space available to you in your shop floor. Assembly is done by manually operated assembly lines. Human beings perform the assembly operations. Assembly A plus B, joining of part A to the part B is A plus B. The product A plus B is obtained. So this is called as assembly operation. How do you join A plus B? You can join permanently or you can join temporarily. Temporarily joining by means of adhesive, by means of fastener, by means of rivet. Any temporary joining can be used to join the two parts. That's how the joining is done at various places. Okay, and usually the part is transported from one point to the other point by means of a powered conveyor. Or some of the workstations may be equipped with portable power tools, and some of the places where the gravity is being used to make the part to move from one point to the other point, where the part is assembled and pushed. When it is pushed with that force, it moves to the next station, and in the next station the part is the base part is stopped and again parts are added and it is pushed, it goes to the next station. Like that assembly is done. These are all typical characteristics of manual assembly lines. Factors favoring use of assembly lines are high and or medium demand of product. When you go for this kind of line is when the demand of the product is very, very high and the assembly operation is simple. You can do this kind of things. Like you cannot do the same thing for machine tool assembly. Machine tool assembly is not a simple task. Where machine tool assembly, machine is kept at one point on from all sides the assembly is done, and for assembling the total time taken for assembling of machine tool would be in months or weeks together. Whereas the lines that we are talking about are the simple product where the production rate is very high. Like in 1 hour you can do 60 assembly, 20 pieces of assemblies. If you can do it in 1 hour, that's what. If you take a TV assembly station, normally production of TVs, maybe several thousands of TVs are produced in one day, and in a 16 hours of shift, several hundreds of TVs are assembled. These are all typical products where assembly lines are used, and it is a need of the discussion of the hour. Products are similar or identical, that favors the assembly, and total work content can be divided into work elements, and to automate assembly tasks is impossible. Whenever the assembly tasks are not automated, you can go for manual assembly task. Why assembly lines are productive? Because we use specialized labor. When a large labor is divided into small tasks, each task is assigned to one worker. The worker becomes highly proficient or efficient at performing that particular single task. So his learning curve with high efficiency. And interchangeable parts. Each component is manufactured to sufficiently close tolerances that any part of a certain type can be selected randomly for assembly with mating part. It is called as interchangeability of the parts. Thanks to interchangeable parts, assemblies do not need fitting of mating components. You need not make the parts exclusively for assembly. The parts, suppose A wanted to make A and B to be assembled. A is one component, B is one component. Any number of components of A can be placed, and any number of component B are manufactured independently, and any part of from A group and any part from B group can be taken and assembled. This is what is called as interchangeability. You cannot manufacture a specific part for specific assembly. So in this, let us discuss certain definitions before we go for the design of manual assembly stations. What is called as workflow? Each work unit should move steadily along the line. This is called as flow of work or workflow. Line pacing. Workers must complete their task when a certain cycle time, which will be the pace of the whole line. When the workers are standing across the line, when the line is moving slowly, the workers are supposed to complete the assembly, and as per the assembly time only, the pace of the movement of the work part is fixed. Accordingly only the speed is set, and by the time a work part comes to the vicinity of the worker and it leaves from the vicinity of the worker, he has to complete the task given to him. Otherwise, you will get incomplete assemblies. A production line that consists of a sequence of workstations where assembly tasks are performed by human workers. Products are assembled as they move along the line. At each station, a portion of the total work content is performed on each unit. Base parts are launched onto the beginning of the line at regular intervals. This is called a cycle time. Workers add components to progressively build the part. You can see in this, starting base parts, red are base parts, and Each is an manual assembly station, we call them, served by several human beings who are experts in performing that particular task. When the work part is moving, assembly is done, and at the end you will get the completed assembly. The production rate of an assembly line is determined by its slowest workstation, because you have to set the speed according to the slowest workstation. That's how the slowest workstation only will dictate the entire line speed, and thus the production rate depends on the slowest workstation. Assembly workstation is nothing but a designated location along the workflow path at which one or more work elements are performed by one or more workers. You see here in the typical manual assembly line, two assembly operators working on an engine assembly line. This is a Ford Motor Company, where assembly of a Ford motor is done. Assembly workstation, a designated location along the workflow path at which one or more work elements are performed by one or more workers, as we had seen previously. This definition already given. Once again, to stress upon that only, this is given. Typical operations performed at manual assembly stations are: adhesive applications, sealant applications, welding applications, spot welding application, electrical connections, component insertions, press fittings, riveting, snap fitting, soldering, stitching, stapling, threading, etc., etc. So many things can be done at different work elements. There may be more than one worker per station. Utility workers are not assigned to specific workstations. They can be used throughout the work. They are responsible for helping workers who fall behind and relieving for workers for personal breaks. The utility workers will replace the workers at workstations. If the worker at workstation gets any personal needs and some personal time, he may be relieved for that. Utility worker will do his job for some time. Maintenance and repair, the utility worker will do. What is the manning level at assembly station, which can be easily determined by a formula given below. Average manning level is equal to M is equal to WU plus sigma I is equal to 1 to N WI by N, where M is the average manning level of a line, WU is the utility workers, number of utility workers who are assigned to system, and N is number of workstations, and WI is number of workers assigned to specific workstation, let us say workstation 1 to N. And total number of workers divided by total number of workstations gives you the manning level, or number of human beings per workstation. Work transport system in manual methods. Manual methods only are used in manual assembly lines to transport the work part. The manual methods are: work units are moved between the workstations by workers without powered conveyor. And in this, lot of problems are there. Like is starving and blocking phenomena happens. Starving, if the previous stage workers takes more time, next stage workers, they don't have any work to do. That's how they have been keep on waiting for the work to receive from the previous station, and this phenomena is called as starving phenomena. Sometimes if the previous workstation is keep on doing the work and pushing the work to the next workstation, and the next workstation people are not able to complete their task, and the work pieces or the assemblies get semi-assembled work assemblies goes on added to that and block that. This is called as blocking phenomena, blocking of station. The operator has completed the task on the current work unit but cannot pass the unit to the downstream station because that worker is not yet ready to receive it. This is called as blocking, and thus this person is not able to do the work further. To reduce starving, use buffers. To prevent blocking, provide space between upstream and downstream stations. But both solutions can result in higher WIP. Whether it is starving or blocking phenomena, both of them results to increase in the work in process inventory, which is uneconomical, which is not supposed to be maintained. We must maintain as less as possible the WIP. The work transport system, mechanized by mechanism, means you can use continuously moving conveyor, operates at constant velocity. Work units are fixed to the conveyors. Work moves alongside the line and back. Work units are removable from the conveyors. Synchronous transportation, intermediate transport or stop and go line. All work units are moved simultaneously between the stations. That means all the work pieces will be moved and stopped. And the stop is to an extent of the time that the slowest worker will perform the operation. And again it moves. The previous work pieces will be moved to the next workstation for the operations. So there the transportation is intermediate transportation, where stop and go kind of line, belt conveyors or roller conveyors or moving finger type conveyors or several other mechanisms for this kind of operations are in use. Problems are incomplete works, excessive stresses are not common for manual, because if any worker is not able to complete a given task in the given time, the work will be transported to the next station without completion of the assembly. There it leads to incomplete assembly. Asynchronous transport, a work unit leaves a given station when the assigned task is completed. Variation in work tasks times, small queues in front of each workstation, you can find it out. Coping with product variety, single model assembly line, you can have a single model assembly line where every work unit is same. Batch model assembly line, BMAL, or multi-model line, two or more different products can be assembled, or products are so different that they must be made in batches with setup between. Or mixed model assembly lines, where two or more different models, differences are slightly, so models can be made simultaneously with no downtime. Advantages of mixed models over the batch order models: no production time is lost during the changeovers, high inventory due to batch ordering are avoided, production rates of different models can be adjusted as product demand changes. And disadvantages of mixed models over batch order models are each station is equipped to perform variety of tasks, and scheduling and logistic activities are more difficult in this type of lines. Alternative assembly systems are a single station manual assembly cell. It consists of single workplace in which the assembly work is accomplished on the product and some major subassembly of the product. Assembly cells based on worker teams. It involves the use of multiple workers assigned to a common assembly task. Automated assembly systems use automated methods at workstations rather than human beings. These can be type 1A or type 3A assembly manufacturing systems. Let us see the analysis of a single model line. The assembly line must be designed to achieve a production rate sufficient to satisfy the demand. Demand must be equal to production rate or cycle time. Let us say annual demand is DA, must be reduced to an hourly production rate of RP. RP is equal to DA by 50 SW by HSH, where SW is number of shifts per week and HSH are number of hours per shift. And if you have 50 weeks in 1 year, then this is RP is equal to the hourly production rate, and DA is annual demand and which can be easily calculated. RP can be easily calculated using this formula. Line efficiency. We can easily calculate the line efficiency as uptime proportion, which accounts for lost production time due to equipment failures or power outages or material unavailability and the quality problems, labor problems, etc. You may need to stop the line for more time, and thus we need to calculate the line efficiency. And the line efficiency can be calculated as if you know the line efficiency, we can easily calculate the cycle time, or if you know the production rate, we can calculate the cycle time also. And production rate RP is converted into a cycle time TC, accounting for line efficiency E. So TC is equal to, normally if line efficiency is 100%, it is 60 by RP. RP is equal to number of parts per hour, and TC gives you number of minutes or whatever it is, and E gives you the efficiency. If E is 100%, it is 60 by RP, otherwise E must be less than 1, where 60 converts hourly production rate to cycle time in minutes, and E is proportional to uptime of the line. Cycle time TC establishes the ideal cycle time is 60 by TC, as we have discussed now, and RC is more than RP. RP is, this is production rate in cycle time, and RP is real production time, and normally RC is more than RP because line efficiency is less than 100%. RC and RP are related to E. So E is RP by RC. Number of workers on the production line we can easily calculate as W is equal to WL divided by A and T, where workload is equal to WL, which is equal to RP into TWC, where available time is equal to AT, and which is equal to 60 into T. WL is equal to 60 E into TWC by TC, where the theoretical minimum number of workers, assuming workers spend all their time on the product on the line, is determined, can be determined as follows: W star is equal to minimum integer, which is greater than TWC by TC, where TWC is equal to total work content time and TC is equal to cycle time minimum per worker. If we assume one worker per station, then this gives the number of workstations as well. Theoretical minimum not possible. Repositioning losses, we can discuss that some time will be lost at each workstation in every cycle for repositioning of the worker or the work unit. Thus the worker will not have the entire TC each time. This leads to line balancing. Line balancing problem is not possible to divide the work content time evenly among the workers, and some workers will have an amount of time that is less than TC. Thus uneven sharing of this time at different work contents or work elements will lead to the line balancing problem. Task time variability. Inherent and unavoidable variability in the time required by a worker to perform a given assembly task. Quality problems, defective components and other quality problems causes delay and rework that adds to the workload. Repositioning losses occurs on a production line because some time is required each cycle to reposition the worker, the work unit, or both. Reposition time is TR, and service time is equal to time available each cycle for the worker to work on the product, and TS is equal to maximum of TSI, which is nothing but TC minus TR, where TR is the repositioning time and TC is the cycle time. And repositioning efficiency is equal to TS by TC, TC by minus TR by TC. If TR is 0, repositioning efficiency is 100%. That means he is not wasting the time for repositioning himself. Components of cycle time at several stations on a manual assembly line are typically shown here. Here you can see it here. So this white portion shows the leisure or ideal time. Ideal time. This ideal time you can say it is a leverage time, and this time can be used for repositioning purpose. And here in this workstation, there is no idle time, and this is going to be the bottleneck machine. This is called as a bottleneck station, where the time is very tight, and prior to that lot of slack and time is there, and the work parts gets blocked here, and the workstations after this will be starved. Line balancing problem, let us now discuss. It's given that the total work content consists of many distinct work elements. The sequence in which the work elements can be performed is restricted. The line must operate at specified cycle time. Then the problem is to assign the individual work elements to workstations so that all workers have an equal amount of work to perform. Line balancing problem is concerned with assigning the individual work. Two important concepts in line balancing are the separation of the total work content into minimum rational work elements and the precedence constraints. This is the total work content. The total work content is a sum of minimum rational work element times, and that is called as total work content. And TEK is the smallest time, indivisible smallest time, minimum rational work elements and the precedence constraints. This is the total work content. The total work content is a sum of minimum rational work element times, and that is called as total work content. And TEK is the smallest time, indivisible smallest time required to complete a given work element. And N is number of work elements. Total number of N is and each NE takes TEK, then sum of that is equal to total work content. The total work content must be given to various station. Though the assembly of all operations cannot be performed at only one station, so it is several stations are divided, and each station certain work elements are performed. And while doing this, while assigning these work elements to each workstation, you need to follow the precedence constraints. At the same time, the total work content at each total work element at each workstation should be more or less equal. Suppose if the total WC is equal to 4 minutes, and if you have 4 workstations, and it is expected that each workstation can spend a maximum of 1 minute for that, and if the work elements are assigned and it takes only 1 minute, it is perfectly balanced line. If it is not 1 minute, then if something is 70 seconds and the other one is taking 90 seconds, then like that it is there, then it is called as unbalanced line, and it leads to several starving and blocking phenomena which is not desired in a typical assembly line. The station service times must added up to the total work content time. TWC is equal to this sigma k is equal to 1 to n TSI. Now precedence constraints, you can see that the precedence constraints are followed, otherwise it won't lead to a complete assembly. The variations in assembly times that make it difficult to obtain equal service times for all stations. There are restrictions on the order in which work elements can be performed. These technological requirements on work sequence are called precedence constraints. You can see a typical precedence diagram here, and the element 3 and 4 can be done only after 1. This is called as precedence relation. And element 9 can be done only after 6, 7, 8, which in turn can be done only after 3. 3 can be done of 3 and 4 can be done only after 1 and 2 or 2. Okay, this is how the precedence constraints must be followed. And balance efficiency is equal to balance efficiency is equal to EB is equal to TWC by divided by W into TS, and balance delay is equal to D is equal to W TS minus TWC divided by W into TS. Note that EB plus D is equal to delay in this should be equal to 100%. The three factors that reduce the productivity of a manual assembly line are line efficiency E, repositioning efficiency ER, balancing delay EB. Labor efficiency on the assembly line is the product of E, ER and EB. More realistic value for the number of workers on the assembly line is a minimum integer W star, which is more than or equal to RP into TWC divided by 60 EER EB, or TWC divided by EER take 2 is equal to TWC divided by ER EB TC, or is equal to TWC by EB and TS. If the manning level is 1 for all stations, then the number of stations is equal to the number of workers. N is equal to W by M. We know that. And total length of the manual line L is equal to sigma I is equal to 1 to N into LSI, and feed rate, we can easily calculate what is the feed rate. FP is equal to 1 by TC, and center to center spacing between base parts is SP is equal to 1 by FP into V into C, or VC into TC. Thus, tolerance time, that means the total amount of time that is available in a workstation near to the workstation zone, is equal to TT is equal to LSI divided by VC. Our ratio is equal to TT divided by TC, which is should be equal to 100%. Lapse time is equal to ET is equal to L by VC, or N into TT. The line balancing objective: to distribute the total work content on the line and the assembly line as evenly as possible among the workers. Minimize the delay WTS minus WTWC, or minimize the total delay sigma E I is equal to 1 to W TS minus TSI, subject to 1. Sigma TEK is less than or equal to TS. 2. All precedence requirements are obeyed. To do this, there are several methods or several algorithms or several tricks have been developed in the literature for the line balancing problem. The first one is the largest candidate rule. The second method is called as Kilbridge and Webster's method. Third one is ranked positional weights method, or RPW method, also known as Helgeson-Birney method. And let us discuss some of them in the following contents. In the following description, assume one worker per one workstation. Let us discuss the largest candidate rule. In the largest candidate rule, list all work elements in descending order based on their TEK values. Then start at top of the list and select the first element that satisfies the precedence requirement and does not cause the total sum of TEK to exceed the allowable TS value. When an element is assigned, start back at the top of the list and repeat selection process. When no more elements can be added to the current station, proceed to the next station. Repeat the steps 1 and 2 till all elements have been assigned to as many stations as needed. So this is how you can see that in this station 1, 2, 4, 5 can be added. Station 2, 3, 6 can be added. Station 3, 5, 8 and 10 elements are added. If you take the total time is here for station 2 it is 0.81, and for station 3 is 0.98, and like that for all the stations we can calculate. The station 1 element is now 2514, station 2 36, and station 3 810, station 4 elements 7 9 are assigned, and elements 11 12 are assigned to station 5. Arrange that's how the physical layout of workstations and assignment of work elements to the stations is done according to largest candidate rule. If you see here, the elemental time at each station supposed to be equal to 1, but it is not because of this total variations. Total time for this is different, for this is different, for this is different, for this is different. This is unavoidable. So if we have the total work content time is 4 minutes, and here there is going to be a delay because the total number of stations are more here. Now next is Kilbridge and Westers method. In this Kilbridge and Westers method, the kind of activity that we have to do is arrange work elements into columns according to their position in the precedence diagram. Work elements are then organized into a list according to their columns, starting with the elements in the first column. Proceed with the same steps of 1, 2 and 3 as in the largest candidate rule. So in this you can see this here. We can draw lines as columns. This is here, this is here, these elements falling in third column, these elements fall in fourth column, like that. After this, assign these elements 1 and 2 first to this till it exhausts the total time for each station. Till that you can go on adding these elements. Then go to the next set, allocating these elements to the various stations. But automatically from one column to other column, if you select, the precedence relations are followed, and thus the automatically precedence constraints is not violated, and assignment is done. This method is Kilbridge-Westers method. And the other one is ranked position weightage method. A ranked position weightage method is calculated for each work element. RPW for each element K is calculated by summing the TE values for all of the elements that follow element K in the diagram plus TE K itself. Work elements are then organized into a list according to their RPW values, starting with the elements that has the highest RPW value. Proceed with the same steps 1, 2, 3 as in the large candidate rule. Other considerations in a line design. Methods analysis. To analyze the methods at bottleneck, other troublesome workstations. Subdividing work elements. Sharing of work elements between two adjacent stations. Utility workers. Changing workhead speeds at mechanized stations, and pre-assembly of components, and etc. Storage of buffers between workstations. It permits continuous operation of certain sections of the line when the other section break down. To smooth production between stations with large task time variations. Zoning and other constraints need to be considered, and parallel stations can also be considered in this to reduce time at bottleneck for stations that have unusually long task times. Alternative assembly systems, we can look into that. Single station manual assembly cell, a single workstation in which all the assembly work is accomplished on the product or on some major subassembly. Common for complex products produced in small quantities, sometimes one of a kind. Assembly by worker teams. Multiple workers assigned to a common assembly task. Advantage is greater worker satisfaction. Disadvantage is lower than line production. These are all the various assembly associated tasks we can consider, and at the end of this talk we can summarize like that. In this we have studied various manual assembly operations, and design of assembly assembly lines, the number of manning levels required, number of workers were required at each station, and the various efficiencies and that are required, and the line balancing problem we have studied, various methods of line balancing. So this completes the total discussion on manual assembly line. We will take some of the time for automated assembly lines. Thank you very much for this. అయిపోయిందా?